In this video, we're going to use the GNU debugger to debug an assembly program. The program is a game. It's an assembly game. So we're going to build and link an assembly program, and then we're going to run the program to see if there's a problem. Hint, there's actually a problem in the program. So we're going to run the program and see if we get an error, and when we do get an error in the program, we're going to debug the program using the GNU debugger, GDB. So the first thing, so we have our assembly here at shaksim3000.asm. It is supposed to be an assembly, a game, a Shak game, I guess from the title. So we can look at the code using nano, and this is just assembly, lines of assembly. So the first thing we do is to build and link the assembly program using NASM and LD. So NASM is the network assembler and LD is the GNU linker. And when we do that, it's going to give us an executable file, which we will then try to run. So this is our executable. And when we run the program, we get a segmentation fault. So what is a segmentation fault? A segmentation fault is what happens when your program tries to access memory that it does not have permission to access. So the memory might not exist, or the program might not have the necessary permissions. It might be privileged memory. So what we know from this is that our program has some area in memory where it tries to access some forbidden memory. So what we do is we're going to open our program in GDB, and we do this by typing GDB and the name of the executable program. So this is the interface of GDB. And the first thing you want to do is to set the disassembly flavor to Intel, and also set disassemble next line on. We set the disassembly flavor to Intel to specify that we're using the Intel architecture instead of AT&T, and we set the disassemble next line on so that it can allow us to skip to the next line or something. So when you run info file, we get information about the files of the program, and as you can see in this case, we get information about the architecture being used. So we had the 32-bit architecture, and we also see the entry point of the program and where the text and data is. Where the text is where the actual instructions of the program are, and then .data is where the data is. So we're going to set a breakpoint at the entry point of the program, and what this does is that it will run the program up to the breakpoint and then stop, and then it will allow us to look at changes and everything going in the program. So we set a breakpoint, and when you run the program, it is going to stop. The breakpoint is at the entry point, so the program doesn't really run. When you try to run it the first time, it's going to stop like it does here. So the program stops running at the entry point. Basically, it pauses before it starts. And after pausing the program at a breakpoint, GDB allows us to examine the files of the program, the registers, and memory, and to see what is going on in the program. So one of the first commands we can run is info reg. The info-reg command gives us information about registers. In this case, we want to look at the EIP register, which is the instruction pointer. The instruction pointer points to the next instruction that is going to be executed by the CPU. So in this case, when you run info-reg EIP, we get the next instruction that is going to be executed by the CPU, which is what was contained in the instruction pointer. In this case, we have our address 804.9000, which is actually the breakpoint. Remember, we set the breakpoint at the entry point of the program, which is the 804.9000. So the instruction pointer register is telling us that the next instruction that is going to be executed is that one. So you can also get more information about the commands in GDB using the help command. So for example, we want to examine memory. I know that the X command can be used to examine the memory addresses. So when I type help X, I can get more information about the options that are available for the command X. And in this case, as you can see, we have X, which is used to examine memory, and we have the address. Address is an expression for the memory address to examine, and format. So we can specify different formats of how we want to display the information from the memory. So as you can see here, we have octal, we have X, we have decimal, and the others. So the first thing that I'm going to do is examine the EIP register, the memory, or what is being contained in the EIP register. This command specifies that we want to view the memory, to examine the memory, and we want it in the hexadecimal format in bytes. We pass the instruction pointer register, and the output that it's going to give us is going to be the actual stream of bytes that will flow through the processor, which will cause the execution of our machine instruction. So it's going to give us the contents of the instruction pointer register. And so these are the bytes that are going to be executed. But we want a more readable version, something closer to the instructions that we typed. And to do that, we can use x/20i, and the I is just telling it to give us the instructions that the actual instructions that are in the register. So when we examine the memory, the instruction pointer again, using this option, then as you can see, we have you can recognize some of the code from the program, from the ASM file that we saw earlier. We can also execute the program step by step using the step I instruction. When we run the step I instruction, it will execute exactly one assembly instruction. So the next instruction that is going to be executed, exactly one. As you can see here, when we run step I, the previous instruction is going to be executed. So in this case, the instruction that was in the address OX804.9000, which was move ESI OX16, so move hexadecimal 16 to the ESI register, is the one that is going to be executed. So after running step I, as you can see here, we have an instruction that has been printed. So the printed instruction is the next instruction that is going to be executed, and by the processor. So the arrow here indicates that this is the next line of assembly that the processor is going to execute. Now, if we want to execute this next instruction, we can just press enter. When you press enter in GDB, it is going to rerun the last command that you use. So in this case, we use step I. Now, when you continue pressing enter, it is going to rerun the step I command. And so this is what is called single step in the program. Basically, we are running the instructions step by step. like while you were looking at it in real time. So when we run the instruction and we stop at this address, so the next instruction to be executed is an int instruction. Int instructions cause the operating system to do something for us. So basically calling into the operating system so that it can do something for us. And in this case, if you look at the other registers, what they've been initialized with, you can see that the EX register has been initialized with hexadecimal 4. So this is how we make system calls. System calls are invoked by loading function numbers to the EX register. In this case, the EX register has been loaded with the number 4, and this is the syswrite identifier. Basically, we're requesting the system to allow us to print something. So we want to write something to the screen or something like that. So in this case, the EAX register has been initialized with 4, and if you look up, we have the EBX register, which has been initialized with letter 1. This is a system call. We are just requesting to write to the console. So the next instruction that is going to be executed is the int instruction at this address, and we can examine the memory at this address, and we can look at the ECX register. So we can use the X command on GDB to examine the ECX register, and remember the X command is used in this format. So you have X, and then /, and then the format of the data that you want to look at, and then the register, the address, the location that you want to look at. So in this case, the register, we want to look at the ECX register. So we can type X /s and ECX, and this means that we want to examine the memory at ECX register, and we want the output to be a string. And when we do that, we can see the string inside the ECX register. So next, we can use the SI command to execute the int instruction. So that is the next instruction to be executed. And when you execute this, we receive a segmentation fault. So the instruction causes a segmentation fault, and hence our operating system terminates the program at this memory address. So the next thing we're going to do is to check the problematic statement in our assembly source code. So we quit GDB by just typing quit and pressing enter, and we can go back to our assembly code by typing nano and then the name. Now in the assembly code, the problematic statement that we have is this int 80. So in our source code we have int 80, and when you look at the same code running in GDB, it has int or x50, which is int hexadecimal 50. Now, as mentioned earlier, int is used to make system calls, so to call into the operating system. But when we write int 80, which is 80 without the 0x, this is decimal, and when we write int 0x80, this is hexadecimal. So the problem that we have here is the writer of the program wrote int 80, which 80, when translated to hexadecimal, 80 is decimal, so when translated to hexadecimal, it becomes 0x50. Int 80 specifically calls into the operating system on Linux, but when you say 80, you mean hexadecimal 80. The author of this code wanted to write hexadecimal 80. So we can fix this by going back to our code, and instead of having int 80, which is int decimal 80, we can write int 0x80, which is int hexadecimal 80. So we can fix this, and let's see if this fixes our program and see if it will run. We build and link the program again, and let's run it again. we have another segmentation fault. So now we can go and try to read the program in the program file itself, and try to find where the bug might be, or you can just take it to GDB and run it and see where the error is. Yeah, so we're going to do that. So I'm going to forward through this. This is the same thing, just set the disassembly flavor to Intel, set the disassembly next line on, and so by setting the breakpoint at the last place the program stopped, so we can use the continue command to execute the whole program now. And this is like the opposite of single stepping, so it will just execute the whole thing. And when you do this, yeah, we have a segmentation fault. So now we know the location at which it happened, the address at which it happened. So we can try and examine the problem here. So the command, so you can actually identify the next instruction from the program file, and what it wants to do is to move some value into the ECX register. So we have a double word pointer. I guess this means pointer that we want to move to the ECX register. Now, if we go to the program file itself, this is what the error is. It's an addressing error. So when the programmer wrote that they want to move into ECX the value OXFFFFFFF, they meant to do something different. Now, the difference between using the square brackets notation and not using the square bracket notations is the difference between trying to access a value and trying to access the memory at that value. So in this case, when the programmer said move into ECX or XFFFFFFF, what they meant to say was that they wanted the value or XFFFFFF to be moved into the ECX register. But because they used the square brackets notation, this was interpreted as the programmer wanting to access the memory or XFFFFFFF and not the value. So the programmer wanted to use the value, but by using the square brackets notation, they used the memory address and not the value. And this memory address, this is very, very far into the CPU. So anyway, so we can fix this by just removing the square brackets notation. And when you remove the square brackets notation now, what this means is that we want to move the value or X and then into ECX. So then now we can run the program again. So build and link it using the same process. And now when you try to run it, will it run this time? Will it? No. have another seg fault. So yeah, let's look for the problem. Let's try this again. Let's do this again. So we can run the program again in GDB, and this time when we run the program, let's try and catch where at which address the program stops execution. And this is the address. So, and you can see the instruction is, it was another int error, so like the first one. Yeah, and you can go back and fix this, and you can go back and fix this in our program. Build and link it. Yeah, and now when you run the program, this is our game. This is the final trial. This is the last attempt. And when you run it now, it's okay. It's going well. Yeah, and no, we don't have a seg fault. So yeah, we have a good game in our hands. Join me again in the next video for SharkSim 4000, where we're going to build SharkSim 4000, and